just, instead of taking the derivative of like the pattern,
why couldn't we just take it as a summation?
Yeah.
Okay, so there's 2 reasons why I didn't just take the derivative of this. So first of all, I wanted you to get a feel of how to find the pattern. Okay, I want you to get practice on that because you do need to know it for this section. And 2, because normally, as I've taught you, when we take the derivative, we increase the index by 1. Okay? In this case, though, we are not, if we are going to take the derivative of this, we are not going to increase the index by 1. And so I didn't want to do it this way because I didn't want to confuse you. Okay, but in this special case, we don't increase the index by 1. So that's why I figured not to do it that way. I'm just going to do it that way. Okay? Any other questions? Do you want to know why we don't increase the index by 1? Okay.
Sure.
So if we took the derivative of, say, this, okay? We took the derivative, we use power rule, okay? And so the reason we increase the index by 1 is because when I plug in n equals 0, we just have 0 anyways. So we just want to get rid of that. We'll just change the index to 1. However, here when we take the derivative, we pull down the 2n plus 1, and when we plug in 0, that's not 0. The whole term is not going to be 0. That's why we don't increase the index when we take the derivative of this. But normally, when we take the derivative of power series, we do increase the index because this is just 0. Okay?
So is that for like all series though?
No, that's why I didn't want to confuse you and go over the head.
So that's just like one special.
Right, that's just like a special case that usually you do have to increase the index by 1 because you will get 0 when you plug in n equals 0. Okay? So that's why I decided to write up the terms. So you don't get confused. We always increase the index by 1 when we take the derivative. Any other questions?
So now that we know like when to change the index to 1 or when to keep it 0, can we just take the derivative of the series and not?
If you remember that you don't change the index for this, then yeah, you can do it that way.
Okay.
Okay. And yeah, so the sine and cosine are very similar. Okay, so if you forget one, you can just take the derivative to get to the other. And so now I'm going to show you a way to memorize which one is which. Okay? So we're going to draw the sine and cosine curves. Okay, so do we all remember what even and odd functions are? If you don't, then maybe this won't be helpful. So even function is when it's symmetric around the y-axis, right? The y-axis is providing a mirror for the function, so we can flip this over and it'll overlap. It'll be the same exact thing, right? So cosine is an even function, right? Even just means it's even, it's symmetric about the y-axis. An odd function is symmetric around the origin, so sine is odd. Okay, so we can remember, if we remember that cosine is an even function, okay, and sine is an odd function, well, sine has odd exponents and odd factorials, and cosine has even exponents and even factorials, because cosine is an even function. Okay? Another way we can think about this is because sine has an I, and an I looks similar to a 1. So here, we're adding plus 1. So 1 and I, cosine doesn't have an I, so we're not adding plus 1. Okay? Any questions? All right. And oh, lastly, this series is very similar to the tan inverse series, right? The only difference is that tan inverse looks like this. So there's no factorial on the bottom. Okay, so be careful about which one you're dealing with here. So tan inverse is without the factorial, sine is with the factorial. Questions? Okay, so now we want to find the Taylor series of sine of 3x squared. forgot to write that in the notes. It's about x equals 0. So anytime you're asked to find a Taylor series, you always need to be told what it's centered around, okay? So this one is centered about x equals 0. Yeah?
If like sine and cosine weren't centered about x equals 0, would they be different? Or would we just have to plug in?
The series would be different, yes. Because remember, the center means what's being subtracted from x before raising it to the exponent. Okay? So here, if we have the center is 0, so it's a Maclaurin series, okay, and we know the series for sine, then we can just use a shortcut again. Okay, so we use shortcut. And again, we can only use a shortcut when it's centered around 0. In this case, it is. So we know that sine x is a sum from n equals 0 to infinity, negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Oh, and you can remember the difference between sine and tan inverse, because sine has an I and also has a factorial, so it's an upside down I. Oh.
Clever.
Yeah. Now you will never forget it for the rest of your life. Okay, so now I want to find sine of 3x squared, so I just replace x by 3x squared. So the sum from n equals 0 to infinity, negative 1 to the n times 3x squared to the 2n plus 1 over 2n plus 1 factorial. So here, we just replace x by 3x squared.
How likely is it that there'll be a really nice problem like this on the exam?
It's possible.
Yeah.
No, seriously. So there was an example where you had to use a shortcut on the final last semester, but a lot of students didn't recognize they had to use a shortcut, and there was only like this much space, and so they thought they actually had to do the 4 steps out, and let's just say it got really, really messy. So no one to use a shortcut and one not to, but it is possible. I haven't seen the final yet, so I don't know. Okay, and so here we don't need to simplify this and break it up because it'll get messier if we do, because then we would have 3 to the 2n plus 1 times x to the 4n plus 2, and that just makes things really messy because the exponent is already messy. So we'll just leave that as is, especially since there's no negative. We just leave it. Okay? Yeah?
So that if x equals a different number, we have to be forced that to do.
Yes, exactly. If we're centering around something else other than 0, then we need to do the 4 steps. Okay? We can never use a shortcut. Questions? Well, I think I am going to get ahead of this in this section than my others. I guess that means you guys are not asking as many questions today.
We have to ask questions.
Okay, so here, right, this one we can actually use the remember, so when we find a Taylor series, we're finding a Taylor series because we cannot use the geometric series formula, right? So, for example, this one we can't use a geometric series formula. It's not of the form a over 1 minus r. Okay, this one we can actually do that. Okay, we can just remember yesterday when we found power series, sometimes we use derivatives and integrals. Okay, so we can actually use derivatives to figure out the power series for this using the geometric series formula, but we would have to take the derivative twice. And we probably don't want to do that, it's going to get really messy, so it's probably just easier to find the Taylor series. But either way, you're still going to find a power series, and either way, it's still going to be correct. Okay? So we can always use Taylor series instead. Alright, so let's do that then. So step 1, find the derivatives.